am making a serious effort to go away from this problem, that is to escape from multi-axial fatigue. For many different reasons, I keep working on it, and actually the real reason behind this experimental or this theoretical work is because I got a very pushy stimulation from Commission 13 of the International Institute of Welding, because right now in weldments this seems to be one of the hot topics. So basically, but when moving to very thin structures, of course, cyclic plasticity plays a very important role, or at least it can play a very important role. So this is the reason why I have involved Professor Harm Askes in this work, because he has done a lot of work on plasticity and in particular on the numerical ways of modeling plasticity. And actually we are cheating here because this was the original idea, a preliminary investigation, but Professor Askes is an extraordinary researcher, so working with him is a great pleasure. So we ended up with a paper which got accepted as it stands, so it's already available in International Journal of Fatigue, and everything came out, let's say, by chance. The idea was something like, let's do this preliminary investigation. But thanks to him, actually, we got this paper. So the idea is extending the use of our multiaxial fatigue method to the fatigue assessment of steel and aluminium thin welded joints subjected to multiaxial fatigue loading. So let's start from the approach itself. I mean, I have already presented this idea a few times, so I'm going to present the approach itself very quickly. So basically the modified Euler curve method is a classical critical plane approach, where the critical plane is the one experiencing the maximum shear stress amplitude, and the fatigue damage depends on two stress components: the shear stress relative to the critical plane here, and the stress perpendicular to the critical plane. So this is the idea. And actually we assume that we can take into account the combined effect of these two stress quantities through this stress ratio, and it's an adimensional quantity, and basically this ratio is seen to be sensitive to the presence of non-zero out-of-phase angles. This means that this quantity is sensitive to the degree of non-proportionality of the applied load history, but as it is defined, this quantity is not sensitive to non-zero mean stresses. And actually this is the hypothesis which is usually formed when dealing with as welded joints. And actually, let me say that I started working on this subject together with Roberto a few years ago, let's say. And actually it was my first research meet on this specific subject, and we are still working together, thank God. So, and basically the idea is that fatigue damage then depends on the range of the shear stress relative to the critical plane, as well as on this strange or particular stress ratio. So fatigue damage can then be plotted in a non-conventional Wheeler diagram, which plots the range of the maximum shear stress against the number of cycles to failure. And basically the idea is that as ratio rho w changes, different curves can be plotted in this diagram. But in general, we have two curves are available, that is the torsional one and the uniaxial one. So basically, since we have just two curves which can be used to calibrate the method, the idea is that, I mean, we have to estimate somehow the position of any other curve. And since in this schematization, given a curve, its position can be defined through the reference stress defined in the high cycle fatigue regime plus its negative inverse slope. By using the two calibration curves which are usually available, we can estimate the position and basically the reference stress and the negative inverse slope of any fatigue curve, where by using simple linear relationships, where these four constants actually can be calculated from the two curves that are used to calibrate the approach itself, that is the uniaxial and the torsional one. So basically, if you consider a welded joint subjected to a complex system of time variable forces, by performing the appropriate stress analysis, and of course this is the tricky point, and we are going to talk about the type of stress analysis which can be performed in a few minutes. So basically, given the critical stress state at the weld, we can post-process this stress state by determining the stress quantities relative to the critical plane, so that we can calculate rho W, and as soon as rho W is available, through the calibration equations we can define the corresponding the position of the corresponding fatigue curve, and finally, from the calculated value of the shear stress range relative to the critical plane, we can estimate the number of cycles to failure. So basically, it's nothing but the conventional approach as formalized by Wöhler, I would say, a few years ago. But as far as welded joints are concerned, the real problem is, or the real question is, how can we perform the stress analysis? Of course, the most simple answer is performing the stress analysis in terms of nominal stresses. And this is what, for instance, Eurocode 3 suggests. Use the nominal section to calculate the corresponding nominal stress. But this approach is very powerful when designing standard welded joints, but of course, if we have to design very complex and unusual welded geometries, I mean, sometimes it's nearly impossible to properly define the nominal section. This is the reason why, over the last 10 years, let's say, a big effort has been made in order to develop local approaches. And in particular, there are two schools of thought, I would say. And the first one is the German one, and they say that the stress analysis has to be performed by rounding the weld toe with a fillet radius equal to 0.05. And this value applies to thin welded joints, that is, joints having the reference thickness lower than 5 millimeters. Or, this is the approach I have developed working in collaboration with David Taylor in Trinity College. Or the idea is performing the stress analysis by considering the stress at the given distance from the assumed critical point. And actually, being fully inspired by the work done by Roberto Tovo and Paolo Razzarin, the assumption here was that the notch, the radius here, must be taken equal to 0. So basically the idea was handling a singularity. And from an FE point of view, you can understand that it's much easier to model something like that rather than putting a fillet radius everywhere to model the profile of the weld bead. And this holding through, especially when joints having complex geometry are involved. So these are, anyway, the three strategies we can use to perform the stress analysis. So now the idea is combining our multiaxial fatigue criterion with these three different strategies which can be used to calculate the necessary critical stress state. Well, of course, we have a multi-axial fatigue criterion. We have different strategies to perform the stress analysis. The only way to understand if the approach works is using some experimental results. And basically we got several experimental results from the literature, and in particular this is the first geometry which was considered. And basically these experiments were run at LBF in Germany, and as you can see here, the thickness of the welded joint in the gauge length area is very small, from 2 millimeters down to 1 millimeters. So very, very thin welded joints. And this is the schematic profile of the weld seam. And here you can see the strategy which can be used to define the stress state according to the reference radius idea. And this is the way suggested by LBF itself. On the contrary, this is our simplified strategy. We consider singularity here, we go a bit away from the singular point, and we pick the stress at a given distance from the singular point. After considering this welded geometry, we moved to two other geometries which are a kind of standard. These samples were tested in TWI, and the thickness of the critical area is equal to 3.2 millimeters. And as you can see yourself, the first investigation, the experimental investigation we have considered was done in LBF, and the second one in TWI. This tells you how important performing the fatigue assessment of thin welded joints is, and this is the reason why these big institutions are investing so much money onto that, because it's very important, for instance, in automotive applications. And finally, we consider this third geometry, again a very thin welded joint made of aluminium. Okay, first problem, let's give the first try. Okay, let's try to use the nominal stress-based approach. So the idea was here calculating the reference stress at 2 million cycles for the uniaxial and the torsional fatigue curve from the experimental results, to compare these values to the ones supplied by both Eurocode 3 and IIW. And what came out is that you can't use those standard values to design thin welded joints, because those results were generated by testing very thick joints. So if you used those recommended curves, you would end up performing a non-conservative assessment, largely non-conservative. So the only idea then was using the numeric scale suggested by Eurocode 3 and to reinterpret the experimental results. So the idea is saying, okay, if we have a standard curve which is specifically designed to deal with thin welded joints, so assuming that at least we have a standard code available, can we use these pieces of information to design joints, welded joints against multi-axial fatigue? And basically, these are the results we got. Basically, these two diagrams plots the experimental number of cycles to failure against the estimated number of cycles to failure. And as you can see here, considering both in-phase and out-of-phase biaxial situations, the conventional nominal-based approach can be used together with the modified Euler curve method to perform the multi-axial fatigue assessment of thin welded joints made of steel. And basically the same conclusion applies also to the aluminium case. Again, estimates which are highly accurate. So the real question, the real problem now, and the real suggestion back to the IIW is, guys, you have to invest a lot of money to develop a new standard code specifically devoted to the fatigue assessment of thin welded joints. Because if we can if we can have something like that, we can perform also the fatigue assessment, multi-axial fatigue assessment straight away. After that, we moved to the German approach. That is, we started using the sorry, I don't know, but the picture is very bad. We started using the reference radius concept. And unfortunately, let me see if we can get something a bit better. Okay, it's a problem of resolution. So basically, this is the curve suggested by LBF to design thin welded joints made of steel by using a reference radius equal to 0.5. Basically, they suggested this one. And as you can see, okay, for one specific configuration, that is for the samples tested at TWI, the curve is quite accurate, but for the other results generated under axial loading, the curve itself is highly conservative. And the situation becomes very critical when moving to actually to the torsional case, because as you can see, this is the recommended curve, and the experimental results are really away from the recommended curve. So the design is too conservative, and obviously it's a big problem, because the idea of using thin joints is because, of course, these big companies want to reduce the weight of their components. So if you supply companies with curves that are so conservative, for sure they end up having for no reason components which are very big. So there is no point in investing in new technology to properly design thin welded joints. And the situation is even worse when aluminium welded joints are involved. This is the curve recommended by LBF, and these are the experimental results under axial loading. And the situation under torsion here speaks itself. So from a design point of view, this curve is nothing but a disaster. So basically, but anyway, this is what the Germans want us to do. So let's give a try. Let's try to use their curves, and as you can see, what we get is nothing but a cloud of experimental points. But we can't ask a method to be accurate in predicting something which is very complex if the calibration curves are inaccurate. So that's the real problem. And of course, the Germans are not happy about it at all. It's not my problem right now. So eventually, we moved to the critical distance or the point method-based solution. So as I told you, the idea is modeling the weld bead, assuming that the radius here at the weld toe is equal to 0. We consider as reference path the bisector of the notch, and the stress to be used to perform the fatigue assessment must be taken at the distance mdv from the critical point, which is equal to 0.5 millimeters for steel and to 0.075 for aluminium. So as soon as the stress at the critical distance is known, we can calculate the corresponding rho value, and from these calibration functions, which are based on a huge amount of data, we can estimate both the negative inverse slope of the appropriate curve and the reference stress to define the necessary modified Wheeler curve. And of course, we got a similar diagram for aluminium. I mean, the reasoning behind these two diagrams is fairly articulated. I mean, it took me at least 2 papers to describe it, but this is what we get. So considering a variety of welded joints, any type, both a uniaxial and multiaxial situation. Again, other geometries here. A variety of loading path, and of course in this case all the geometries were characterized by the thickness of the main plate being larger than 5 millimeters, so thick welded joints. This is the accuracy we get. So in total these two diagrams summarizes more than 2,000 experimental results generated by considering, I would say, at least 25 different geometrical configurations. But we are still talking about thin welded joints, the white points. But what happens when we apply the same strategy to thin welded joints, that is the gray points here? And as you can see, we get at the same level of scattering, even if the thickness of the main plate or tube of the welded joint is very, very small. So basically, by taking the critical distance value constant, we can predict the multiaxial fatigue behavior of welded joints having the reference thickness varying in the interval from 1 millimeter up to 100 millimeters. So the scale effect is there. And actually, but a question, of course, comes out naturally, which is a very cruel question, because we consider the stress at the given distance, and of course what we do is a conventional linear elastic analysis. So we are forcing our material to obey a linear elastic constitutive law in a region where plasticity plays a very important role. So I don't have any answer right now. I mean, Hamascus has an answer and he's working on it through gradient mechanics, and basically the idea is trying to show some equivalent behaviors between the elastic material and the elastoplastic material, but honestly the work is still in progress. But at least from an engineering point of view, we can end up saying, okay, you can use the point method based solution together with the modified Weller curve method to design welded joints having a thickness which ranges from, let's say, 1 millimeter up to more than 100 millimeters. So, coming to the conclusions of the presentation, I would say that we can still use the nominal, classical nominal stresses to perform the multiaxial fatigue assessment of thin welded joints, but the real problem is that we need founding bodies willing to invest money to define the appropriate standard curves to be used to design thin welded joints, as it was done in the past for thick welded joints with, for instance, Eurocode 3 and Eurocode 9 and the IIW recommendations and so on. So when moving to the reference radius concept, I mean, the real problem is that it can work provided that the appropriate calibration curves are available, and those supplied by LBF are not accurate enough, so they have to do a bit of extra work to supply their customers with more accurate curves. And finally, as far as local stresses are concerned, the overall best accuracy is obtained by applying the modified Weller curve along with the point method. And basically, we can estimate fatigue lifetime independently of both thickness and degree of multiaxiality and non-proportionality of the assessed load history. So, thank you very much for your attention.